In this short video, I will show you how to set up the Agilent InfiniVision 3000 and 4000 X-Series oscilloscope to perform eye diagram mask testing on a differential CAN serial bus signal. The first step is to download the various CAN mask files that Agilent provides on our website. These mask files are available at no charge. After storing the appropriate files to your USB memory device, insert it into the scope's front panel USB device port. The next step in making this measurement is to probe the differential CAN bus. Agilent recommends using the N2791A differential active probe. Now also available is a special probe head adapter that can be used to directly connect this probe to a DB9 sub-D type connector. For our demonstrations, let's first look at a CAN signal in a standard non-eye diagram format using an Agilent 4000 X-Series DSO, and then we'll perform the eye diagram test. Here we show the scope triggering on ID 025. For this measurement, we have probed this signal with our differential probe such that the scope displays dominant bit low. The first thing to note here is that we are seeing various dominant bit low amplitudes. The bits that are going the lowest are acknowledge bits. The bit that you see near the middle of the scope's display is evidence of arbitration between two nodes in our system. Although we can't see it yet, there are also some timing shifts associated with these particular bits since they are being generated by asynchronous nodes. But an eye diagram test will overlay all bits on top of one another to show us all amplitude and timing variations. To execute an eye diagram mask test, we'll begin by pressing the Save Recall front panel key. Next, select Recall, then navigate to the appropriate mask file. In this case, I'm going to recall a 500 kilobit per second mask file based on dominant bit low probing. When you recall this file, the scope will automatically set itself up to randomly capture and overlay every differential bit of every CAN frame based on a unique clock recovery algorithm that emulates worst-case CAN receiver synchronization and sampling. With all bits overlaid on top of one another, we can now see worst-case amplitude variations as well as timing jitter. But the jitter that you observe in a CAN eye is not the typical random timing jitter you see in most other eye diagram displays. Most of the apparent timing jitter you see in this measurement is actually worst-case propagation delay of the CAN signal traveling from one end of the network to the other and then back again. During testing, if the signal crosses through any part of the pass-fail mask test region, failures are clearly marked in red, as you see here. Also, take note of the fast update rate and mask test statistics. This scope is capable of testing over 200,000 waveforms per second. To learn more about Agilent's new InfiniVision X-Series oscilloscopes, contact your local Agilent distributor and ask for a demonstration. Thank you.